Have you ever wondered how a cold pack works? Like you're out playing sports and you injure your ankle and someone comes over with the first aid kit and gives you one of these. You find the little pouch inside and you break it open like that and switch it around and wow, it gets really cold really quickly. We've all been there, right? We're icing our ankle and the whole time we're wondering, how does chemistry make cold packs work like this? How does simply mixing urea and water actually make the thing turn really cold? Turns out there's a whole lot of chemistry in here, and it involves something called the heat of solution. When I add sodium hydroxide to some water in my fancy calorimeter, the temperature goes up. On the other hand, when I add ammonium chloride to the water in my calorimeter, the temperature goes down. So what's going on here? Why does the temperature go up for one and down for the other one? Turns out this temperature change is the result of a phenomenon called the heat of solution. When something dissolves in water, there's very often an energy change associated with that. Sometimes energy is given off and the water heats up. Sometimes the energy is taken in by the solute and the water cools down. So what is this heat of solution? And is there a way to calculate how much heat is absorbed or released when something dissolves? The answer is yes, and we're going to get into it right now. So what is this heat of solution and how can we make sense of it all? First, let's think about the formation of a solution, particularly a solution in water. You may have learned that water is polar. Water has a bent shape. It has a more electronegative oxygen side and a less electronegative hydrogen side. And when an ionic compound dissolves in water, you'll get cations and anions, and the oxygen side is going to cozy up next to the sodium or the cation, and the hydrogen side is going to cozy up next to the anion. And these attractions release heat. You may have also learned that the formation of a chemical bond or an attraction like this does release energy as the atoms and molecules move to a lower energy state. And so there is a definite release of heat when those ions get hydrated in a solution. Those ions, again, are called the solute. The water is called the solvent, and the resulting mixture is a solution. Now, these aren't the only energy changes that happen when a solution is made. We're going to talk about two more. There are three separate energy changes needed to dissolve something, and the sum of these changes results in something we call the heat of solution. The three energy changes that have to happen when an ionic compound dissolves in water are as follows. First, it might make sense that if you're going to make a solution with a solute, you have to separate the solute molecules from themselves. They come as probably a little crystal, and you have to separate those ions. And actually, energy needs to go in order to separate the ions. So that's energy going in. You also have to make a little room between the solvent molecules, separate those from each other so that the ions can then get in there in between those solvent molecules. And that also requires energy to go in. So these first two steps, energy has to go in order for that to happen. But then the magic happens. The solute and the solvent start forming those interactions where the water molecules, in this case, are going to surround the ions and make those attractions, and that releases heat. So these first two absorb heat, energy going in. The last one releases heat, energy going out. And we have a little enthalpy diagram, energy diagram, to show how these might have an imbalance. Sometimes, if you have to put in just a little amount of energy to separate the solute particles and then separate the solvent particles, but when they get together, they release more energy than you had to put in, then overall you would have an exothermic heat of solution. So when it's exothermic and the temperature of your water goes up, that means we're getting a lot more energy back than what we had to put in. On the other hand, if we have to put in a ton of energy to separate the solute particles, maybe they have a really strong attraction to each other, and we have to put in energy to separate the solvent, and we only get back a portion of that when the solute-solvent interactions happen, then it's going to be a net endothermic process. We had to put in more than we get back at the end. Now, all three of these are happening. It's just a matter of which side is winning. The endothermic side, putting energy in, or the exothermic side, taking energy out. Let's do an example similar to one you're likely to see. Let's start by just reading the prompt. If 3 grams of potassium hydroxide are added to 100 milliliters of water and the temperature goes from 25 up to 32.3, let's calculate the heat of solution for potassium hydroxide. So note, first of all, the temperature is rising. And so when this stuff dissolves, what we're going to be getting is more energy back from the solvent-solute interaction than the energy needed to put in to separate the K and the OH and the water molecules themselves. So we're going to have an exothermic heat of solution, and it's going to end up being negative. Now, here's the formula you would use to find the heat of solution. Heat of solution is simply the amount of heat given off or absorbed divided by the number of moles. And we would give that in joules per mole, or most often kilojoules per mole. Sometimes you'll be told how much heat. Maybe there's 3.4 kilojoules given off, and you know how many moles it is, so you just divide it. Other times, if you have lab data, you're going to have to find the amount of heat. And we do that by doing Cm delta T, or heat capacity times mass times the change in temperature. And then we'll divide by moles, and we'll get joules per mole, which we can convert into kilojoules per mole. Just to clarify, we're going to use the heat capacity of water. And even when we make a solution, it's not going to be pure water anymore, but most of it is going to be pure water. So you can go ahead and assume that the heat capacity of water is 4.184. We will use the total mass of the solution, however, because the solute and the solvent and the solute are going to be heating up together. And so we want to put the total mass for a little bit better result. And we always do final minus initial when we do temperature changes, so that we end up with the appropriate sign at the end. An exothermic process should be negative because energy is being given out. An endothermic process should be positive. And so we have this negative sign to change that. And so if I'm seeing this problem, I might go ahead and say, all right, this is my formula. I need to go ahead and put in the heat capacity of water, which is 4.184 joules per gram degree. It's always good to write down the formula you're using and then substitute it in with units, so the person reading your work knows that you know the units and the formula you're using. So it's pretty good. Now, 100 milliliters of water, I'm just going to make a quick assumption that that's going to be 100 grams of water. It's going to be pretty close depending on the temperature. Let's go with 100 grams of that and 3 grams of that. So 103 grams total are going to be heating up. And the final temperature is 32.3 degrees Celsius, and the initial temperature was 25 Celsius. Okay. Now, when I'm doing these, you can, I like to just convert to moles in place inside this formula. You can convert to moles separately, however you feel that you want to do it. But I would just do something like this. 3 grams of KOH. This is all going to go on the bottom. And I know that 1 mole of KOH has a mass of 56 grams. And that will get me a certain number of moles. I'll multiply the top, divide by that small number of moles. And when I do this, I get a delta H of 58,500 joules per mole, or 58.5 kilojoules per mole on that. And so that would be my answer that I would report. And of course, I would make the little box around it, put a little heart next to it, so that anybody reading my work can find the answer easily from that. Okay, we have a pause the video moment. All right, we have a similar question. Example number 2 on heat of solution. This one is ammonium chloride. We have 5 grams, and the temperature is actually going down. So take a moment, pause the video, and see if you can find the heat of solution for ammonium chloride, and I'll see you back here in a couple seconds. All right, and if you found that this is a positive value, 15 kilojoules per mole, by the way, let's go back to my original example. That should be negative because it is exothermic. All right, sorry about that. But this one ends up being positive, and you get about 15 kilojoules per mole if you multiply heat capacity, mass, and the temperature change over the number of moles of ammonium chloride. So if you got that one, great job. And now let's do a slightly different one, similar to one you might see, though, on an AP exam or something like that. In this case, we're actually going to know what the heat of solution actually is. So we're going to try to find an actual amount of heat. So for example, example 3, the heat of solution of ammonium nitrate is positive 25.4 kilojoules per mole. So it's positive, it tells me it's endothermic. How much heat is absorbed when 25 grams of ammonium nitrate are dissolved in water. So if you know what your delta H is, your heat of solution, this would also work for a heat of reaction or something like that. You're going to convert to moles if necessary. So check your amount, see if it's in moles. If it's not, convert it into moles. And then you can simply multiply by your delta H, which if it's in kilojoules per mole, will get you your answer in kilojoules. So we're going to go ahead and do this two-step problem. So 25 grams of ammonium nitrate. Okay. And again, make sure you're showing your work and your units. We're going to change that into moles. 1 mole of ammonium nitrate is 80 grams. I went to the periodic table and added all those up. You can check my work if you'd like. And then we're going to take that delta H right there, and that's going to go in as my second conversion factor. So 25.4 kilojoules per 1 mole of ammonium nitrate. And if I do that right, I get 7.94 kilojoules out of it. And that's going to be a positive value. So the grams is going to go away, the moles is going to go away. I'm left with kilojoules, and that is the amount of heat for that particular sample. It would give out 25 kilojoules for every mole. I don't have an entire mole, so I got less heat overall. But convert to moles and multiply by your delta H. Okay, we have our second pause the video moment, a very similar question. The heat of solution of sodium hydroxide is negative 44.5 kilojoules per mole. If 8 grams of sodium hydroxide are dissolved, how much heat will be absorbed or released? Take a moment, pause the video, and I'll see you back here in a couple seconds. Okay, and if you got a value of negative 8.9 kilojoules, that negative simply means it's being given off. Then congratulations, you did a great job on that one. So there you have it, a little bit of theory and a little bit of problem solving involving heat of solution. I hope you found it helpful. If you have questions, you can send them to me directly or in the comments. And in the meantime, happy studying and have a great day.